welcome to another lecture on molecules in motion. So, what we are going to discuss today is summarizing what we have done previously. In the 30th lecture, we had talked about the Fick's first law, and since this is the basis of whatever we are going to discuss now or in the forthcoming lectures. So, I would like to recapitulate what we had talked about in the lectures previous. So, in previous lecture, particularly one which is the 30th one, we had seen how the Fick's law of diffusion, we are talking about diffusion of particles here. Essentially, we are talking about particles which were previously taken as charged, and now we are going to look into how they are going to behave under certain conditions if there were not charge or not under an electric field. So, what we had seen in the 30th lecture was the Fick's law of diffusion, that means migration of ion through a medium, where the particle flux can, whenever we talk about flux as particles, we are talking about movement of matter. So, it can be either represented as a flux of matter or it can be represented as a flux of particles. So, both of them is actually going to mean the same. Sometimes the matter or particles will be represented in terms of the number of molecules, sometimes in terms of the number of the amount of the material that can be expressed in concentration. So, the flux of particle or matter from according to first law of diffusion of the Fick's first law of diffusion is proportional to the concentration gradient, and how this Fick's first law of diffusion is proportional to the concentration gradient could be deduced from the kinetic model of gases, which was taken much earlier. Then how it can be deduced more generally was what we had done in the 30th lecture, and how it can be applied to diffusion of species which are in the condensed phase. So, condensed phase means it is going to be the solid states, solid particles in liquid medium. So, here what we are looking into, we are looking into the flux of diffusing particles that is in motion in any spatial direction x, y, z in response of a particular thermodynamic force, and this thermodynamic force which we had derived in the last class was due to the concentration gradient. And for a very dilute solution, the thermodynamic force which was supposed to be existing for the particles to move from one region to the other. When we talk about the Fick's law of diffusion, we are essentially talking of moving of the particles or the molecules or the ions from a high concentration to a low concentration region. Here we are not going to talk about any charged particle, we are going to talk about any particle in general. So, the thermodynamics force which was derived in the last class for a very dilute solution, where the conditions are limiting conditions, where you have the activity coefficients to be 1 and the activity approaches the concentration unit. So, when the activity coefficient is 1 and the activity is approaching concentration, that we are calling as almost a dilute solution, a very dilute solution or a ideal solution. For that, the thermodynamic force which we derived in the last class was given by, this is the thermodynamic force which is equal to R T by C and the gradient in concentration at a given temperature and pressure. What we had talked about in the last class was this force is not essentially a force per se, but it is a driving force towards having towards the possibility or towards the conditions of towards a hunt of the maximum entropy for the system. So, when we are approaching a system is according to second law, the system supposed to be going for the highest order of disorder, only then we have a system which is at equilibrium or stable. So, this is the thermodynamic force which we had derived, which was a negative gradient of the concentration at a given temperature and pressure condition. So, if you recall, what was how we defined as the flux of particle diffusing through a say any axis z of a container, which was found to be the negative gradient of the number of particles or the number of the concentration. Here, if we talk about the number of particles, then we say the flux of particle which is flowing through the medium is proportional to the gradient in the number density. Okay. We are talking about a z direction. This direction z is actually, if you can see this, if you can see this diagram, you can see this diagram. I have a region where this n is high. Here, this is the axis where you have the number density, and this is the axis where you have the spatial coordinate. We are taking this as z. We are taking this as z, assuming this is the container, and we are talking about a condition where I have a window through which the particles are passing, and I am having observation, or we are looking at that particular window. When we are talking about a window, we are essentially talking about a point where you have the origin. Across that window, you will have minus and plus z. Minus z is this direction and plus z is this direction. If you can see this, if I imagine this as the window, then if I am moving towards this side, I am moving towards the positive z, and if I am moving towards this side, I am moving towards the negative z. Clear? So, what we are having here, if you just have a closer look at this, I can easily represent this z by x and say this is my x coordinate. Okay. So, if any direction, if I say this is the z, I define this as z, but I can take this as x as well. Okay. I can say represent this as y as well. What I want to say is along the direction which we are moving is parallel to the container we are looking into. Okay. So, the parallel conditions apply, and the window is the place where you have the center of the axis. From that window, you can either go towards plus of that axis or minus of that axis. And what does it essentially mean? Let us go into what we are meaning. So, we have this flux of particle, we have a flow of matter down a concentration gradient. According to Fick's law, the particles are going to move from high concentration to a low concentration region, and the j, if j has to be positive, then what we have the slope has to be negative. It's the slope of number of particles with distance. This distance is any axis, any spatial coordinate x, y, z parallel to the container we are watching. Okay. So, what do we mean by saying this? The flux is positive when the gradient in the number density or the number of particles or the concentration of particles along a particular axis is negative. See, the flux is the number of particles. So, the number of particles moving through a window at a given through a given area at a given unit time cannot be negative. That term cannot be negative, because you are counting the number of particles. So, particles cannot be negative. So, what does a negative or a positive sign mean? The negative and positive sign mean that if I have a positive value of flux, that means I am moving towards the positive direction z. Okay. If I have a negative flux value of flux, what does it signify? It does not signify that particles are negative. It signifies that the flux of matter is moving from the window which we have seen taken as the origin of the coordinate spatial axis from towards the negative side of that. So, if you look at that, what I mean is, when is going to be the, when we are saying that the flux is going to be positive. Flux is going to be positive when we are moving, this is the origin, when we are moving towards the positive z direction. When we are moving towards the positive z direction, if you see, if we are moving from the positive z direction, then the slope of this curve, is always negative. How is the slope negative, or how do we calculate the slope? The y coordinate, y final minus y initial divided by x final, x initial. So, the distance which we are saying taking is increasing, x direction, that means the z denominator is always increasing, final will be higher than the initial value, because we are moving towards this side, we are gaining the distance. So, the final distance will be always more than the initial one. So, the denominator will be positive. But what happens when you are having the number of particles? You see the number was higher here and you are having a lower value here. So, when we are moving towards x, we are gaining in the distance. So, the denominator of the delta y by delta x, denominator of this slope is going to be positive, but the number, you see the final number is going to be always less than the initial number. So, since the final number is going to be less than the initial number, the dn value will be always negative. So, if dn value is negative, then the slope which is given by dn by dz will be negative. So, when we are moving towards the positive z direction and we are saying that the flux is positive, then the slope of this is supposed to be negative. Okay? And since it is a negative gradient of the concentration, so the flux becomes positive. Okay? So, what we have here, so from the coefficient, from the proportionality equation which we have taken that the flux of particle is a negative gradient of the concentration or number density. This negative gradient is always going to be a positive term, because this the ratio will become a positive term only when this becomes negative. Okay. So, what we have seen, when we are moving towards the positive z direction, then we are getting a flux as positive, because the slope is negative, then the whole thing becomes positive. So, the flux becomes positive when we are going from a higher region of concentration of particles to a region where the concentration particles are lower, right. So, if I keep this relationship, the flux of particle or matter is proportional to the number gradient in number density, negative gradient in number density, then I can put a proportionality constant, and this proportionality constant makes the equation something like this: the flux of particle equal to d into the concentration gradient or number gradient. or particle number density gradient. So, this is what we call as the diffusion coefficient, and the diffusion coefficient is can be the number of particles or number of moles, whatever the in concentration unit, per square per meter square per second. Okay, that is the unit we have. So, what we have now, you can see that if from this diagram you can see that this is the window we have, and we are moving towards a positive direction of x, or we can say this is nomenclated as z. So, we can say take it z. It does not matter whether we say x, y, z. It is actually a direction which is parallel to the container. If we designate the container to be parallel to in the x axis, we can write it in the x. It is any along any one of the spatial coordinates. Okay. So, it is not necessarily that it has to be z, it can be x, it can be y, any one direction which is parallel to the container. Okay. So, if you remember, how do we define the flux? And this is what we had done when we are doing the kinetic theory. When we are talking about a flux of matter, we are talking about a particle moving with a speed, certain speed, which we call that drift speed, which is a steady speed, terminal velocity or terminal speed in any particular direction x, y, z, that is parallel to the container. When the thermodynamic force mass this drift speed is obtained, when this thermodynamic force matches the viscous force, only then we attain the speed, the drift speed. So, they are moving with the drift speed s when the thermodynamic force is balanced by the viscous force of the medium, passing through an imaginary window. This is the imaginary window of area A at in time delta t. So, the total number of particles, which is the total number of particles passing through the window, if I want to find out the flux, I have to divide it by the area into the delta time. So, what is the total number of particles which is passing? Whatever is contained in a volume element, suppose it is moving with the speed s and in time delta t. So, s into delta t is the distance, okay, from Newton's law, speed equal to distance by time. So, distance into time should be giving you the distance, the speed into time should be giving you the distance. So, this distance into the area gives you the total volume element. So, the total volume element, if it is moving towards a distance of s delta t here, then the total volume element along this will be s delta t into A. So, in all the particles contained in the whatever concentration unit you are taking, if you are taking in molar concentration, the total number of particles which are there in the container will be given is given as C into the Avogadro number. That gives you the number density. Okay. So, C into Avogadro number is the total number of particles contained in the volume element this delta S delta T into S into A into the number concentration number density, which is the molar concentration into Avogadro number. Molar concentration is the total moles contained in the total volume of the container into the Avogadro number gives you the number density. This divided by the area into the time delta t gives you the flux. Okay. So, the flux is nothing but the drift speed into the number density. This is moles per unit volume of the container into the Avogadro number. And from the Fick's first law, what we have, the flux of diffusing particle or matter due to flow of particles from high concentration to low concentration region in a spatial direction parallel to the container in response of the thermodynamic force arising out of the concentration gradient will be having a flux of say equal to j equal to d into the number gradient or number density gradient. Okay. So, we have you see two values of j, one from the diffusion and this is from the Newton's kinetic theory explanation. So, these two j values we need to compare the two values. Here we have in terms of the number density, here also we have in terms of number density. So, if suppose I divide both the equations by Avogadro number, then it converts the number density into the molar concentration in moles or in terms of the amount of the substance that is passing or that is flowing. Okay. So, when I divide this part and this part, both the j conditions divided by Avogadro number Na, obviously this becomes Sc and this becomes dc by dx. See, I have taken x now. Okay. I can take z, I can take y, but we are going to maintain x for the sake of simplicity, x being taken in place of z, which should be again parallel to the container which we are taking. So, what we have? We have one condition for where you have the flux of matter or particle, which is in terms of the amount, which is equal to the diffusion coefficient into the concentration gradient. It is the molar concentration we are talking about. Similarly, from this expression which we have got from the kinetic theory of particles moving under an electric field, we had an expression where the flux of matter will be equal to drift speed into the concentration, where c is the molecular speed and s is the drift speed. So, these two expressions we have. Now, both are j, so I can equate these two. Now, if I equate these two, I have a term in terms of the concentration gradient. Now, this concentration gradient, I can replace that by whatever thermodynamic force which we had derived previously in the previous class. What we had derived for a limiting condition where the solution is very dilute approaching ideality, that time the thermodynamic force could be given by RT by C into the gradient in concentration at a given temperature and pressure. So, this value of the gradient in concentration dc by dx can be substituted in this expression of Sc equal to minus d gradient of concentration. This we are whatever we derived as a thermodynamic force, which we are replacing. So, from here what is going to be the dc by dx? It is going to be Fc by RT. So, from this expression we have the S equal to d by c into this, and this we are replacing by what? Fc by RT with a negative sign, because this is a negative sign which we have, and this outside also there is a negative sign. So, what we have come down to? We have come down to a expression of the diffusion coefficient into F divided by RT. Okay. And what is this F? That is the thermodynamic force, and so it is does not matter what is the origin of the thermodynamic force, the drift speed will be always the term in relation to the diffusion coefficient by RT, and the system, according to the system we are studying, we have the defining thermodynamic force. Okay. So, from this we have this expression, we have now a relationship between the drift speed of a particle in motion that can be calculated if we know if we have a relationship between the S and D, then what we can see, if the particles in a motion can be calculated, the drift speed of the particles in motion can be calculated if the F, the effective force, is known and the diffusion coefficient is known. Okay. If these two parameters are known, then I can find out the drift speed of the particle in that particular system. So, it does not matter what is the origin of the force, all we need to know is what is the effective force that is existing. For example, which we have already seen, we have in the case of a ionic solution where the ions are moving under an electric field. If you remember the expressions which we had derived, the drift speed was equal to the ionic mobility, the mobility of the ions into the applied electric field, strength of the applied electric field. Okay. And the force experienced by the each of the ion of say charge Z e, was taken to be what? The total charge Z e into the electric field. The force experienced by an ion was Z e into the electric field. So, the effective force experience will be because of all the Avogadro number of particles which are there. So, Avogadro number of particles, total number of particles into the Z e, and you know F is the Faraday constant, which is Avogadro number into the electric charge. So, this can be replaced. So, we get a simplified form of the total effective force that is experienced by the ions is equal to Z F e. Here F is, see, you have to do not get confused, this is also F and this is also F. The red one is the effective force that is experienced by the particles in the system, and this F is the Faraday constant. Okay. So, now what you do, substitute these in the above expression. If you are substituting this in the above expression, what you get? You have this as the drift speed which we have derived in terms of the effective force. This is the effective force, and from the expression which we have for the S in terms of the this mobility is going to be U into E, okay, the total mobility of the ions into the strength of the electric field. So, I can equate these two, U E equal to d F R T, where remember this F is the thermodynamic force or the effective force on the particles. Okay. So, what we have, we can rewrite this in terms, this E gets cancelled if you are substituting the value of in this expression. In this expression, what you are doing, you equating the two S's, this one and this one. Okay. So, if you are equating this two, then what you get here, you have U E and then you have d F R T, and the thermodynamic force which we have taken is the effective force, that is nothing but Z F E. Okay. So, I have replaced the force here, this is the force, this force I have replaced by Z F E. So, this F what I am having is the Faraday constant, this is not the force which was initially there. So, if you further look into the values, you will see that you have a relationship between the diffusion coefficient and the mobility of the particles in the system, right. So, what we have derived is, we had derived the drift speed in terms of the thermodynamic effective force and in terms of the diffusion coefficient. This relationship we further exploited when we are talking about this example where you have ions moving in a solution under an electric field. If that is the condition, then what is the total effective force? This force was replaced by ZFE, where here the F is the Faraday constant coming from the Avogadro number multiplied by the electric charge, right. So, please remember this, because we are going to be using this relationship in the consecutive relations we are going to derive. So, what does the Einstein's relationship gives us? This is the Einstein relationship, what is in yellow. It gives us information about the diffusion coefficient of a particular particle when the mobility of the particle is known. Okay. So, you have a relationship where you have diffusion coefficient d linked to the ionic mobility. So, we can find out, we can solve expressions to find out the value of diffusion coefficient for a particular ion, which is for which the mobility is known to us. Thank you so much.